Hey, all right. Hey, welcome back here. It is Tuesday now, Tuesday of week number 5. And like I said on Monday's lecture, I want to just lay out every day here at the beginning as we get to the end, as we get into the busy part here of the semester. And so I'll begin here with holding up the syllabus again and saying we're right here, June 16th, the day after test number 2. And we're working in chapter 16. And we are going to then continue that and finish up 16 here and maybe even roll into a little bit of 17. We'll see how it plays out. But we have today's class, which has our 2 lectures. Then we have tomorrow, which has our 2 lectures. Then we hit the weekend, Thursday, Friday, Saturday, Sunday. No classes there. And then we get into this last week. And we'll have a regular day on Monday, but then test number 3 on Tuesday, and then the final exam on Wednesday. And so I just want to keep reminding you that from here forward, test number 3 is from wherever we left off on the last test. So that'd be chapter 15, or 13 is where we left off. So the next test is going to be 15 and then 16 and then 17 and then however far we get. And so we'll just keep going until we get onto that test. And then remember, the final exam is on Wednesday and it's comprehensive. And so I want to just encourage you this weekend, plan your schedule. And like I said before, whatever obligations you have, like work obligations, if you can get somebody to cover that shift, free up this weekend. Because I think the best planning you can do is to have lots of time this weekend to get ready for the exam and the final. And what I mean by that is whatever we get done today and tomorrow, then this weekend, what you can do is all the labs up to this point. You can do all the homework up to the point of the weekend. And you can do a review even all the way back to the beginning. Because see, what's going to happen on Monday, Tuesday, Wednesday is things are going to go really, really fast. And it's kind of hard to believe, but summer school goes fast. And so we have only 1 week and 1 day. And that 1 day is a final exam, so there's not like any lectures or labs on that day. So really we're down to the last week. 1 week from today, you will be taking test number 3. Then there'll be a lecture after that, and then we'll have a final exam the next morning. So it goes quickly. And so with a test number 3 and a final exam on Tuesday and Wednesday, I just want to encourage you to do anything and everything you possibly can. You can even do more and kind of start to learn on your own and do the lectures for week number 6. But that's kind of hard to do. And so what I'm saying here is if you get all that other stuff done, if you got a reviewing for the final exam, plus you've learned this chapters 15 and looks like we'll do 16 and 17 before this week is over. If you did all of that over the weekend, then really all you got to do is learn the new material that's on Monday to get ready for the test on Tuesday. And of course also the lab. Then also all you have to do is learn a little bit more from that last lecture on Tuesday, and then it'll be the last lab on Tuesday. Oh no, maybe I take that back. There won't be a new lab on that Tuesday. I'm going to do what I did before. I'm going to do the test review. That does take away from our lab, but it's been, I think, useful and successful. So I'm going to follow that plan. But you'll definitely want to do that test review on Tuesday as you get ready for then on Wednesday. And then amazingly, we're done. And so not much time left. And so use it wisely, and that's what I wanted to say about the scheduling. I also want to backtrack a little bit and apologize and actually fix. A couple of you sent me an email and I need to fix number 29 on the test. I did the test review and it looks like I made a little mistake, and so I again apologize for that, and I want to fix it now. But the 2 of you who sent me that email, and I responded back this morning that oh yeah, You're absolutely right. So thank you for that. And maybe many of the others of you recognize it. It was such a silly mistake that it was hopefully so obvious for you. But if you didn't see it, let me correct it now, because I might have misled you on number 29, on my solutions to number 29. So let me go back to the test, and I'll just put here on the board number 29. If you remember that from the test, it said that you had a rectangular beam. It really didn't give the third dimension of the beam, so let me not draw it here. But it said the beam had a length of 4 meters, and it had a width of 10 centimeters. Excuse me. And so the first part of this is where I made a little mistake here. I said, well, how many atoms would fit in a vertical column along these 10 centimeters? And like I had done in class, I said this is how you would do your division. This is why you learn division in 4th grade, is you would say, okay, I have a distance of 10 centimeters, and I want to know how many little tiny things, these are atoms, can fit into them. So you take the big thing and divide it by the little thing. And so how many of these little things fit into that big thing here? And here's where I made the mistake. I went to put centimeter, but totally left off the 10. And so this part is missing right there. That's the part that should have been there. So the meters would still cancel off, but you would have 10 times 10 to the minus 2, which is 10 to the minus 1. So then when you divide it by that, you get 10 to the 9th instead of the 10 to the 8th that I got when I did the solution. So this is a billion instead of 100 million. Now, along the length here, that one was still correct. That was the 4 meters for the total length, and the size of the atom is about 10 to the minus 10th, and so that came out to be 4 times 10 to the 10th. So when you were asked how many atoms are on this surface, it would be 4 times 10 to the 10th in length, and in height it would be this billion instead of the 100 million. And so this would make 4 times 10 to the 19th instead of the 18th that I did on the solution. So apologize for that. Hopefully that was the only mistake. It's the only one I know of right now. And then speaking of your exam, I'll point out that I haven't got a chance to grade them. I thought I would get at least a little bit of chance to look at them. Didn't, but I should today, and so I'll start grading them today. They take a little while, so I think tomorrow's lecture, when I get here, I'll have to tell you that maybe I got hopefully a half of them done, and then that would be a good goal for me today, and then I can do the other half Wednesday night to Thursday morning. I know that that's what I ended up grading on the last test. So. Keep an eye on Canvas Thursday, because you'll see your scores there on Thursday. All right, so with all that said, we better jump back into the lecture, and you might recall where we left off. We had just done the first half of the chapter, and we were getting started on the second half. And I said kind of a simple layman's definition of a wave would be something like this, where it says that the vibrations move. And so I said there was something that is moving, and tried to emphasize to you it wasn't an actual object that moved. It wasn't any material that moved. It is the flow of energy. And I'll just show you again here with our little wave machine. And so I've got these rods. And when one rod moves, it is connected to the adjacent one. And so one makes 2 move, and then 2 makes 3 move. And it gives all of its energy. So 2 stops moving and 3 starts moving. And then 3 gives its energy to 4, and the 4 starts moving and 3 stops moving. And then it keeps going like that, giving its energy across one to the next, to the next, to the next, to the next, to the next. And so that's the idea of a wave. And so we classify anything a wave where there's this actual flow of the energy without the flow of the matter itself, the neutrons, the protons, and electrons that we talked about in chapter 11. And so that's our idea of waves. And of course, you heard me say then these next 4 chapters, or really 2 chapters, are about mechanical waves, and then the next 2 after that are electromagnetic waves. And so we've got these 4 chapters on waves, kind of broken into 2 sections, mechanical waves versus electromagnetic waves, which is a big subject in itself because it has to do with our optics. And so if we draw a picture of a wave, we often do this. We say, all right, let's make a grid, and we do kind of this curly thing here. For those of you who have a little bit more math background, let me call it a sine wave, a sine function. That's from our trigonometry class. And that's what I would get if I continued to make these. I was making more of what you would call a wave pulse, where I just made one little hump. But if I continued to do it, they would just move all the way down. Of course, in my case, I run out of space, so they reflect back. And that's some of the stuff we want to talk about, is how it flows, when and why it reflects. But when I draw this, of course, maybe I would put the y-axis up here and the x-axis up here. And of course, it is also a function of time, and so you can't really draw that well on the board, which is why I like these machines, because you can then see that the humps move along here. They flow along here. And this top part, let's just call it the crest. And so I'll say what looks like it's moving. And again, it's not, but it looks like there is some point called a crest that is just moving along at some speed. And so there's really 3 variables that go into the description of this wave. How does it move along the x-axis? How does it move along the y-axis? And then where is it in time as the crests are flowing and moving along? And in fact, this picture, and what I'm showing you, is probably best described, and most people, I think, immediate thoughts when they think of a wave are these type of waves, which I will call transverse wave. Because maybe less common and less connected here to at least the common education, and not a science education, I guess, here, is the longitudinal waves. And so we're going to categorize our waves into these 2 categories. And so let me just repeat what I said yesterday. This is a good chapter, but also a little abstract in the sense that it likes to generalize things. And I hope you see that. And I hope it's not so general that you don't see how they apply to anything. And so he doesn't really say what type of waves. Let me give you some good examples here in just a second. But the definition of a transverse wave is to say that the vibrations, and here's some fancy words, of the medium, so there's the part that I was saying he's a little abstract here, are, and this is the key word, perpendicular to the motion of the wave. And so, like I said, he doesn't really say what's vibrating, and he just says the vibrations of the medium. And what he means here, like for this one, is the medium would be these rods. These are the things where the waves are made. Maybe a better example would be our ocean, and then we would call these water waves. Our medium would be the ocean. It would be the water itself. And so when they vibrate, and so if you watch the water waves, not maybe near shore, but maybe further out, you'll see something like this. You'll see a boat, and the wave will come, and the boat will go up, and then the boat will go down. And so that's a good indication of a wave. First of all, notice the boat did not move left or right. It vibrated up and down. That's this definition of a transverse wave. The median is the water, and the vibrations are then perpendicular to, of course, the surface of the water. And so those water waves out into the deeper part of the ocean, those are our transverse waves. Those are a good example of transverse wave. This machine, again, is a really good example of transverse wave. That's why we call this not just a wave machine, it's a transverse wave machine. And of course I showed you this one also, and I'll show you again. Here is another transverse wave machine. These are the shorter rods. And so they travel much faster. We'll talk about their speed soon too. But this is the idea of a transverse wave. We will soon see when we get into 17, light is also a transverse wave. The vibrations are perpendicular to the direction they travel here. And so that's, again, what most people think. So maybe that's not a big surprise to you. So what's a longitudinal wave? Well, let me save a little effort on my part and not write out every word. I'm going to use the ditto symbols, but now I say it out loud. I probably should pause. You might not know what the ditto symbols are. It goes way back. But when you were writing and less computer and email and typing, if you wanted to indicate to somebody the same as the word above it, you would just make these little ditto marks. In fact, if you want to hear a funny story, I actually learned that in 4th grade. Not one of my better moments, but I was in trouble in school. I think I was chewing gum. So I was caught chewing gum, and I don't think they have this type of discipline anymore. My kids never had to do it, and I know they were in a lot of trouble. So, but we would have to write 100 times, and that would be your recess. And so instead of getting recess, you'd have to get a pencil and a paper. You have to go sit at the table, and you'd have to write 100 times, I will not chew gum in class. I will not chew gum in class. I will not chew gum in class. And it was a very simple punishment, but it was really quite successful. I mean, you did not want to do that. You lost your recess, your hand would cramp and get so sore. Anyways, I'll never forget, I was there, I was sent to the table, I wrote about 3 or 4 lines, I will not chew gum in class, I will not chew gum in class, when a bunch of my buddies come up and say, hey, aren't you going to play kickball with us? And I thought, I can't, I got caught chewing gum in class, I gotta sit here and write it. They go, what, how many times? 100. And they go, oh, you know those ditto marks we just learned in class? And I was like, no, not in my class, maybe in your class. Yeah, it just means copy. So they showed me. And so I just took the whole paper, and I go ditto, 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 all the way down. I got 100 of them done. I thought I was done. I was good. I turned it in. I went out to recess. I played kickball in what was left of the recess, only to get more in trouble when I got back in class. But I was like clueless. I was like, hey, yeah, this ditto thing's great. But anyways, like I said, not one of my finer moments here, but I didn't really follow the whole punishment thing right. But for you guys, this is what I'm trying to say. The vibrations of the medium are, and then this is the key, are, I should just say, in the same direction as, and then I should just put the motion of the wave. And I think written this way, it really emphasizes how these waves are different. I kind of showed this, but let me show you a little better here today. This is our wave machine. Now that I have it out front and I have my cameraman back here today, I can kind of move around and he can kind of zoom in. But this is what we call our longitudinal wave machine. Because again, it's a wave. Watch what happens if I bump this side of it. See, these little rods can oscillate, but they're connected together. And so when I push one, it pushes the next, which pushes the next, which pushes the next. And so down here on this end, the energy does flow. It goes from here all the way down to here. There is actually a flowing of energy without the flow of the material, right? The original rod is still back here. There's the energy, but back here is that original rod. And so because of that, we would call this a wave. And it's a mechanical wave, but it's definitely a wave because the material doesn't move, but the energy does. But you can see that this is a little different. And then you might even say harder to kind of comprehend and understand, I think, than the simpler ones. And so the transverse wave, because the vibrations are perpendicular, you can kind of separate that in your head. You go, okay, well, there's the vibrations in the y direction. There's the motion in the x direction. And so that's just automatically separated in your head. This one's a little harder to see, but it's still nonetheless a wave. It is just the movements is in the x direction, or I should say the oscillations are in the x direction, but then so is the flow of energy. And so when you plot something like this, it's a little bit hard to kind of comprehend, especially when we try to then say that the amount it moves away from its natural place, what we called yesterday its equilibrium spot, is then labeled here on the vertical axis. And then where it is positioned is on the horizontal axis. And so when you do it, you kind of get this shape. And again, this shape can be misleading. This almost looks the same as that. You're like, well, wait a minute, isn't that the same thing? And no, because on the vertical axis, I'm plotting the position it moves on the y. It actually moves vertically. But here, what I'm plotting on the x-axis is how much does it move in a horizontal direction. And so this looks like this might be the same, but they are very different. In fact, maybe I'll spend a moment here showing you a couple of other longitudinal waves here. I brought out the slinky because the slinky, I think, does this pretty well. If I hold it up here, let's see, how much do I need to kind of hold it above my head? That looks pretty good. If I just release one little rung up here, one little coil of the spring, I'm hoping you can see this on video, how this one pushes and then pushes the next and pushes the next and pushes the next. And so eventually down here, it gets crunched together. And so I would say there's a flow of energy. And so the crunchiness of it, you might call it the compression of it, is in a vertical direction. And also the flow of the energy is in a vertical direction. So let me emphasize, this spring and this longitudinal wave machine are both longitudinal waves. Notice, longitudinal does not mean horizontal or vertical. It means same direction. So which way does the energy flow? Horizontally. Which way are the oscillations? Horizontally. That's a longitudinal wave. Which way does the energy flow? Vertically. Which way are the compressions? Vertically. They're in the same direction. So that's a longitudinal wave. You might be able to see it on camera with this one. I know it looks pretty good in a classroom setting, but this is a nice long spring. that if I give it a little tension and I maybe take part of the spring and I compress it and let it go, that little compression pushes on the next, pushes on the next, pushes on the next, pushes on the next, pushes on the next. And you can just see it race to the other side really quick. And then reflect on back. And so, again, this is an example of a longitudinal wave. And as we'll see as we get into the next chapter, sound waves act like this. And so sound waves are longitudinal waves. And so it's kind of one of the first things we'll do in the next chapter is talk about, okay, what are sound waves and how do they behave? And we'll see right away they are longitudinal waves. In fact, if you remember, I said water was a good example of a transverse wave, but I also put a little qualifier on there because transverse water waves is true, but water waves get kind of interesting as they get closer into shore. And that might be where you might experience it. If you're kind of wading into the ocean, you will feel kind of a combination of the two. They are transitioning and eventually they fall over on itself, and that's the breaking of the wave. But when you're standing in the ocean, if I was like facing the waves and they're coming at me, I don't just go up and down. That's what I do when it's not too close to breaking or I'm further out. If I'm just, in my kayak and the wave comes, I go up and then I go down. But if I'm near where it's getting ready to break, but it certainly hasn't broken yet, it'll actually, as the wave gets close, it pulls me into the wave, then it lifts me up, then it lifts me back, and then down. And so it's really a combination of the two together. And so I wanted to emphasize that we like to classify them as two, different pieces. But that doesn't mean you can't have both going on at the same time. And water waves near the shore are like that. They've got a little bit of this back and forth motion, so longitudinal effect. And then they have the vertical effect too. And so that's the transverse one. So both of those can happen at the same time. Well, I probably should move on and not spend too much time or more time on this, but I think you are getting the idea here of what a transverse and a longitudinal wave is. Now, I said the word crest up here, and so maybe now I should actually put it on the board, but these top points, let's call them the crest, and these lowest points on the waves, let's call those the troughs. And so as we talk about our waves, as we make them and we describe them, and as we move into sound waves and light waves, you'll know what I meant when I say crest or trough, and crest being the highest point and trough being the lowest point. But I'd also like to point out that these things repeat themselves. And so if you look from maybe a crest to a crest, but it would also be true a trough to a trough, let's call this then the length of the wave. It's wavelength. And so trough to trough or crest to crest is its wavelength. In fact, any point on the wave that would just get to the next place where it repeats itself is its wavelength. And so if I were to, again, come back over here and make some waves, 1, 2, right there, from the crest to the crest, about that far, that is the wavelength of our wave. And so a new word here that we didn't get in those bunch of definitions that when we started this chapter, things like amplitude, frequency, period, all those we defined yesterday. A new one here is its wavelength. And the traditional symbol for wavelength is the Greek letter lambda. And so we will then use lambda quite a bit in our discussion of waves, including sound waves and light waves as we move forward in these next 4 chapters. And again, I'll point out this is a length. So the units are hopefully obvious. They are meters or centimeters or millimeters or kilometers, whatever the case may be. In fact, I saw a really good TV show Sunday night on Nova about, well, I shouldn't go too far, but it went out to Goldstone out in the California desert and how they were communicating with Voyager and all the NASA satellites. It was amazing to see the satellite. But anyways, they were all picking up things at wavelength of 35 meters. So there was this ginormous wavelength. That's a big wavelength, and so they needed these big dishes and way out there to communicate. But anyways, I definitely caught my attention as soon as they said, "Hey, yeah, this is a 35 millimeter wavelength," and it made me hit pause. I was like, "Then," and so as you'll see here, I'll get out my calculator, and there's some other things you can calculate based upon this wavelength here, and so that was real curious, like the size of the antenna and the frequency. All those things fall into place once you know the wavelength that you're working with. And so I was real curious with that. But again, those are radio waves. But again, I just wanted to keep emphasizing this chapter is a little bit on the abstract side because they don't really want to say what kind of waves these are, but want to emphasize it would be true. This whole discussion we have about transverse and longitudinal waves would be the same whether we're talking about water waves or light waves or sound waves or radio waves or X-rays. It's still that same idea here. Now there are some other very interesting properties about waves. Let me keep going here. And again, let me emphasize that it would be true for sound waves and light waves and radio waves and water waves. And this is a discussion about the interference, or what we call the superpositioning, or what happens when the waves come together. One or more waves, or well, two or more waves come together. I'll start with a picture. Let's say that I have something that looks like this. To make it real simple, I'll just say, what happens if I have a wave? And you might not even call this a real wave because I just made the up. I didn't make the whole wavelength, right? I didn't make the up and the down. Sometimes we like to refer to that instead of a wave pulse, instead of a wave that has a wavelength. But what if I have a second one? And maybe to help with the understanding, I'll give the second one kind of a weird and crazy shape that's not really kind of normal for waves, but more of a square shape to it. And so I got a rounded wave and I got a square wave, and they are approaching each other. What will happen? And so maybe as this one moves to the right, and so I'll put it right here, still going to the right, and then I'll put this one right here, going to the left, and you might say, hey, they're going to hit. And okay, fine, I'll use that word. Yeah, they're going to collide. What happens when two waves collide? But there's really a better word we like to use. What happens when these two waves overlap? Because these are not materials. This is not like a baseball hits a softball. What happens here is this is just energy. You might say pure energy. On my wave machine, this is saying lift the rods up, and the other one is saying lift the rods up. And so when they overlap, collide, if you will, you get something that looks like this. You get, okay, lift the rods up, and then lift it up. And my drawing's not so good, but I'm hoping you're seeing the idea that what would happen is this would just lift up the rods. They don't hit and like deform. Like I said, a baseball and a softball would come together, and as they would crunch, you wouldn't get them overlapping, you would get them colliding. You would get them kind of squishing together. And the baseball would squish a little bit and bounce off, and the softball would come and squish a little bit and bounce off. That's not how waves work. That's why they're in their whole category here. That's why, we got to talk about waves separately than our mechanics. And it gets even better. What happens a moment later? Well, a moment later, the flow of the energy, the rectangular shaped one, continues on its way. And the shape of the rounded one then continues on its own way. So again, that's why the word collide probably is not a really good word. It's an overlap of the two. And so we get a combination of them right here, and then they really just pass right through that. Right? And a baseball and a softball, don't do that. You don't get this. You don't get a baseball coming this way and a softball coming this way, and then they kind of merge into a basketball, and then the softball goes down that way and the baseball goes that way. No. They never merge, and they don't pass through each other. They bounce off, and the baseball comes and goes back, and the softball comes and goes back. That's very, very different than the behavior of the waves here. And so this whole process uses a fancy word, maybe one you've heard before, but it is kind of this 50-cent word that you don't hear much. And so this process is called superpositioning. And superpositioning is just a fancy word by saying, just combine the two together. If you have wave 1, just add it to wave 2. It would be no more than asking, if somebody asked how much money you have, you probably go, oh, well, I'll superposition my money together. Well, you probably don't use that word. What you say is, let me add up all my money. You would say, okay, I'm going to go and I'm going to look in my wallet or my purse and go, okay, I have $3 in my wallet or purse. And then I go, you know what, I've got some change on my dresser, so I got another 50 cents on my dresser. And you go, I think there's a dime that fell out of my pocket and it's under the cushions in the couch. Let me grab that too. And so you would add all those together. You would combine them all together. You would superposition all of your money together. And so you'd have the $3, the 50 cents, and the dime. So you'd say, oh, my total amount